Well, we have another two modifications of the model. The first one, I'm going to introduce the third species. We know in the food chain, the rabbits will eat grass to survive. If there's no grass, the rabbits cannot survive. Then I'm going to introduce the grass into this model. And we make two more assumptions. So the grass, you can think is the lower level prey, and then the rabbits could work as both a prey to the wolf and the predator to the grass. So in such a model, then we add two more assumptions. Each acre of grasses is that's not consumed by the rabbits will grow back in constant rate, just like the population model. And each prey eats a constant proportion of the available grass per year. That's similar like the wolf eat the rabbits. And then all the other four are the same as our Lodogos water system. So once we make this assumption, and we can run the model, and then we can identify three unknown functions. Xt are the grass at the time t, y is the rabbit's population time t, and z is the wolf's population at the time t. And the parameters, we have 7 parameters. At this time, I'm not going to go all the details. And the new parameters, the E, actually is the D, the rabbit's death rate. We did not put into the birth rate, we separated that into the natural death of the rabbits. And F, the A is the new one, the grass growth rate is 0.5 acres per unit of time, depends on how many acres of grass survived. And the B is the grass consumption rate by the rabbits. So that means the rabbits will eat 0.002 or say 0.2% of the grass. So the other 4 are the same. Those are the same as our previous model. So what is the invariant? The invariant is the same thing. The grass at the time t equals the growth minus the chewed down by the rabbits. The rabbits is more complicated. It equals the birth and the eaten by the wolves and also the natural death. And the wolf equals the birth rate minus the death rate. So the mathematics model are very similar. You just have a little bit of change. First, we got a new species. The grass is just like the rabbits before, ax minus bxy. But the rabbits, it acts as a predator to the grass. That's where the cxy come from. And also the victim of the predator is eaten by the wolf. But they also have a natural death minus dy. And then the wolf is the same natural birth by consuming the rabbits and the natural death. So if we put the new initial condition, all the parameters replaced by the constants we know, and that's what the model looks like. So it's a nonlinear 3-variable system. And we can run this. Look, yeah, you have very similar behavior. I only drew, I drew the 3 of them. A periodic phenomenon, and here is the phase plan between the rabbits and the wolf again. So very similar like the previous example. Well, the last thing I want to show you is a little more modification. Let you observe a phenomenon. The new modification of the example is this. I'm going to change the growth rate of grass be a constant instead of the constant times the grass. That means regardless the grass is eaten or not eaten by the rabbits, it's going to grow back. And the previous model, only the survive the grass will grow back. The eaten one won't grow back. I think for grass, this make more sense. And then our initial condition, we have 200 acres of grass and 200 rabbits and 45 wolves. And then we have all these 7 parameters. So what's the difference from the previous one? Just one line difference. This one for the old model is ax minus bxy. Now it changed to a minus bxy. And the second equation, just the first one with all the constants. Now we're ready to run this model. Of course, you are going to run by yourself and change the number. That's a very good exercise. We find a very different phenomenon. This time it's not going to have this oscillation of cycles. Instead, after a little while, and how long I ran? This I ran for probably 30 years. In the end, the population of the rabbits, it's here. It's almost a constant. It's too hard to read. But it's around 5,000 of rabbits. And the wolf is here, is about 100 of a wolf. That's it. And the grass is just come and go with the 5 or 50 acres or 5 acres. So that really is a different phenomenon than here's not a circle and actually span, let me use red color, into a fixed point. And like a spiral, and in the end, it's just end up with a constant, and this is 100, that's 5,000 here. So this is what we call equilibrium point. And also we call it stable, a converged situation. Well, I have some exercise for you to observe and compare the two different phenomena. And finally, let me summarize what we talked in 2 minutes. Well, we talked 3 examples of the traditional nautical Volturian system and the extended system. The 3 files in Stellar is posted on the blackboard, like these 3 names here. You can identify the name and run it, observe it, change the number. That's your exercise. And we talked about 3 definitions besides the nautical Volturian system. Autonomous system, that's when the right hand have no t phase plan equation when you divide the 2 autonomous equations, and the equilibrium points, that's where the derivatives equal zeros. And last, but it's important, we learned how to use the phase plan equation to check the correctness of your numerical solution to the original system. Thank you for today. I will see you in a couple of days.